So we're continuing with points, lines, and planes. When we say that one object contains another, we mean that the second object lies on or is within the borders of the first one. So in this diagram, line AB contains points A, B, and C. Remember, the line continues going. It doesn't stop at A or stop at B. Ray AB contains A, B, and C because that ray, remember that arrow is to remind us that the ray continues going, starting at A, going through B, and continuing. And then segment AB only contains A and B. Now, it also contains a whole bunch of other points in between them that we haven't named, but it doesn't contain C. Now, in this next diagram, this is how we're going to show something three-dimensional. So here we have plane R, and we've got several points on it, and we have a line going through it. So what that line actually looks like, notice that in this region, the line becomes dotted. So in technical drawings, engineering drawings, architectural drawings, all those kinds of things, if there is something behind something else, the way that they'll designate that is with a dotted line, and we do the same thing. So what this looks like is that, so from where you're sitting, can you see all of the pencil? No. That's the part that on this diagram is dotted. So G is up here above the plane someplace. Excuse me. And H is somewhere down here below the plane. Does that make sense? So that's what we're doing on this. So plane R contains points D, E, and F. D, E, and F are all on this plane. G is above the plane, H is below the plane. Okay? All right, so intersection. Typically, when you think of intersection, just in non-mathematical terms, you think of like two streets crossing one another, right? The intersection, when you have two streets, is the part that is part of both of them. So if we have something like this, where we have these two streets that are crossing one another, the intersection is all this part right here in the middle. That is not just part of one street, but it's also part of the other street. So everything that's in here is part of the intersection. So the intersection of two things are what they have in common. I'll give you a different example. So let's see, what should we do for this group? All right, everyone who is taller than, say, 5'7", stand up. All right, thank you. You may sit down. And now everyone who's wearing a black shirt, stand up. All right, thank you. Have a seat. So who is the intersection for that? Yeah, Jose is the intersection because he's part of both groups. Now, the intersection doesn't have to be just one thing, it can be multiple things. So a point or a group of points that two objects have in common is called the intersection. So this is how it applies to geometry. So here, line MN and line JL intersect at K. That point is on both lines. It's not just on one, but it's on the other. Okay, you may notice that you're like, why isn't there a dot there? Well, the reason there's not a dot is because we don't have to put a dot. You can if you want, but most of the time in the book and in the things that I draw, we don't bother to, because there is a point where those two lines intersect. So the line intersection postulate simply says if two lines intersect, they intersect at exactly one point. And in math, when we say something like exactly one, we mean there is one and there's not more than one. And you're like, okay, why don't you just say one? Well, I could say, I know that there's one car in the parking lot because my car is out there. Is there exactly one? No, there's a whole bunch more. But if I say there's one car in the parking lot, that actually mathematically means that, well, there's one and there could be more. Okay? So in math, when we mean there's one and no more than that, we say exactly one, so that it's clear that we don't mean one and maybe more than that. All right. Let's turn over to the next page. So this is how we illustrate two planes intersecting one another. Remember, a plane is just like a flat surface. So here, basically what we have is this giant three-dimensional plus sign. Okay? If you can imagine taking two pieces of paper and cutting them and then shoving them together. You've done that before, right? Or seen something like that? Yes? Anyone know? You kind of know what I'm talking about? Where they go together like this? I'm getting several blank looks. No, or if it's no, that's okay. No? Okay, let me show you. Cheap homemade visual aids. Like that. Okay? This is what that diagram is meant to look like. And notice in this diagram, planes M and P both contain points R and S, right? R is part of plane M, but it's also part of plane P. And S is part of plane M, but it's also part of plane P. And I could put a whole bunch of other points in here, right? All of those belong to both. So their intersection is line RS, because even though we don't show it, remember we talked about this yesterday, that the planes keep going infinitely, right? They're flat and then they keep going infinitely. So the plane intersection postulate says that if two planes intersect, their intersection is a line. So if you think about it, I'm trying to see where there's a good seam. Oh, right up here. Where those two faces of those walls meet, see how you get this nice line right there? That's what we're talking about. That's because the planes are flat, and when they meet, they make a nice straight intersection. So a question for us is, must lines and planes intersect? Notice on both of these, the plane intersection postulate and on the line intersection postulate, it says if the lines intersect or if the planes intersect. So do they have to intersect? Well, the answer is no. There's a couple of different possibilities. Some of them you already know about. So for example, like line TA and line LH in this diagram. Do those intersect? Are they ever going to cross one another? No. Anybody, can you tell me what those lines are called? What's the name for that? Yeah, those are parallel lines. Let me give you a different one. How about line JD and line NH? Those do not intersect. So you have to realize this is a three-dimensional diagram. This is like a box. NH is at the bottom on the front. JD is going up and down in the back. Even though those keep going, one in the front will look like this, the one in the back will look like this. Are they ever going to intersect each other? No. Are they parallel? No, they're not parallel either. So if you give the definition of parallel lines as just being two lines that don't intersect, I go, well, what about these two? Do they intersect? They're like, no. Are they parallel? No. Okay, then your definition is not so good. Okay? And then with planes, let me erase this stuff. I think an easy one to see in the room would be the floor and the ceiling are like planes that never intersect. So how does that translate to this? Well, we could, since they didn't put a italicized letter, we can name the top plane by any 3 points that are not all on the same line. So JRT. Remember that yesterday we talked about the fact that if you have 3 points not all on the same line, there's just one plane that'll go through them. That's why we only need these 3 points to name the plane. So that's the top. So be careful. Students sometimes are so focused on those 3 letters. What other point does plane JRT include? A, yeah, it's the whole top. And then the bottom, let's call that plane HLD. Those do not intersect. By the way, and we'll do more examples of this later, but there are other planes other than the top and the bottom, the front and the back, and the left and the right sides here. You don't need to draw this, but here's another plane. See how you could do, again, you don't need to draw it because it kind of muddies things up, but you can see how that goes diagonally through the box. There's all kinds of other planes. You could use this point, and this point, and right, that's a triangle. A triangle's flat, so that's going to make a plane also. There's an infinite number of planes that are inside of this figure, which is why we don't try to draw them all. Right? It would just be so messy, it would be not helpful at all. All right, next page. So parallel lines are non-intersecting lines on the same plane. That's the part that people leave out typically when they give the definition. They're non-intersecting lines on the same plane. So here, line L and line M are parallel to each other. This is the symbol for parallel. One of the great things about geometry is all the symbols make sense. The symbol for parallel looks like two parallel lines. The symbol for perpendicular looks like two perpendicular lines. The symbol for triangle is a little triangle. I mean, all of them are pretty obvious. You know, there are some things in other math classes where it's just not as obvious. Then those other lines are called skew lines. Skew lines are non-coplanar lines, meaning they're not both on the same plane. It has to be three-dimensional to get skew lines. So here we've got a plane, and we've got this line J that's going through the plane at this point. And here, what's this dotted line mean? It's what? Yeah, it's behind the plane. The plane is between you and the line, right? It's actually going underneath the plane. And then K is up here on the plane. Those two are never going to intersect, but they aren't parallel either. Those are called skew lines. So they don't intersect. But they aren't parallel. And then parallel planes are non-intersecting planes. There's not great ways to draw those, just to be perfectly blunt with you. This kind of gets it across. Your book does a nice job with using different colors and stuff. When we're drawing them ourselves, it's a little bit harder. Or, going back to this diagram up here, you can see parallel planes in that, right? For example, plane THA, which would be this whole plane over here, and plane RND, this whole plane over here. Those are parallel planes. Okay? Any questions about that? Okay, then that's it for today's lesson. Oh, you still have a good chunk of time, so go ahead and get started on your assignment, please.